I'm going to read. Thank you, Jerome. And the first speaker of the day is Poshak Gandhi, who will continue on with the discussion that's started yesterday afternoon. Please go ahead.
Great. Thank you very much, everyone. I really want to thank the organizers again, not only for organizing the hybrid meeting, but really getting the timing perfectly right. It's been so good to help to wipe away the cobwebs from the pandemic. It's been very difficult for many people to get back into research, etc., and this has been really good. So yes, I'll be talking about multi-wavelength campaigns, coordination, thanks to the discussion organizers yesterday, and also later today, we'll be having a similar discussion. I started to list my collaborators in a lot of this work and discussions, but at the end, I found that I was listing out more than half the conference. So I just put some screenshots of all of us in there, because I think all of us are collaborating in this, and we should be thinking about this. It touches upon a point that I want to get to later on. And my presentation is decided to stop. Okay, so we are in September. Is it too early to start talking about Christmas already? If I were to ask you what you wanted for Christmas, I'm sure many of you would say all the sky, all the wavelengths, and maybe messengers as well now, all the time, okay? Not too big a deal, perhaps. Of course, it's very difficult to organize. But I think we should always start with the main science question. We must be driven by the science. And I think that's already been touched upon before. For us, accretion science is inherently multi-scale and multi-wavelength. The multi-scales connect time and size. So in a sense, life is already made, if you want, easy for us that, that all these scales are interconnected. And so the case for multi-wavelength science is inherent to any proposals that we write. But we still do need to make the case, and it doesn't mean that it's easy. And in fact, there are many, many hurdles to multi-wavelength coordination. I've just noted some of these down here in different categories. There are so-called infrastructure hurdles, there's natural hurdles, and there's maybe human hurdles. So in terms of infrastructure, we're really not yet set up to do multivalent science as best as we could be. Timing science, surprisingly, is not always recognized as a priority in many, many missions. One of the biggest surprises in recent times for me was JWST, whose clock is not at all optimized for science. Their minimum timing requirement is 0.5 seconds, half a second over a 12-hour window, which when I first heard about it, I couldn't believe my ears. And relatively small changes could have changed that if they were implemented at the mission inception stage. Coordination infrastructure, for example, not all observatories are even allowed joint proposals. Many do, of course, things are becoming better. Disjoint proposal deadlines, this was discussed yesterday, different proposal deadlines fall at different times of the year. In terms of proposal submission itself, there's the issue of double jeopardy. So, in order to win time on one facility, one multi-wavelength facility, it often helps if we have time on another facility, but the other facility might only give us time if we have time on the other facility. So, so you never know how to actually juggle these different observatories, different wavelengths, etc. TAC expertise, this was also discussed yesterday. If we are writing a proposal, we need to make sure that we appeal to the right people, but can we actually make the case to them? Do we have experts in the time allocation committees who really understand the science? Then, of course, there's natural hurdles, visibility constraints, the Earth getting in the way, uncooperative weather, etc. And finally, there's also human constraints. There's competition amongst us, of course. There's hesitation. Sometimes we just think, should I be going out of my way to collaborate? There's also just laziness. And these are all completely valid, if you want, emotions or psychological behavior. We're all human after all. In order to discuss some of this, this can all be found in this paper, Milton et al., which I'll come to in a minute. And I also put this poll out for you. So thank you to everyone who filled this in. It's actually filled in a little more on Slack if you go and look at the latest updates. And there's also several comments down below, which I encourage you to check out. but I asked you exactly this question of what are the main hurdles to improving coordinated campaigns. And I had several options. Fortunately, none of you said there are no hurdles. We're doing great, which means that we definitely want improvement. All of us do. I think broadly everyone agreed that the lack of multi-wavelength proposal infrastructures is the main factor at the moment, with the other two scoring about half each. So thank you to everyone who filled this in. When campaigns work well, they do work spectacularly well if they are planned well in advance. And nowadays we do have some examples of this, of course. We all know about the EHT collaboration, the LIGO, Virgo collaboration, etc., which have produced a multitude of papers, a lot of great science. Of course, that also results in very, very long collaboration lists, which has its own advantages, perhaps disadvantages, and that's something we should discuss and keep in mind. In practice, outside these major collaborations and formal consortia, etc., how does it usually work? Well, what often happens is that there's a new ATEL or GCN announcing a new discovery, a new transient outburst, etc. And suddenly you might have a few TOOs set up, perhaps, but in terms of multi-wavelength campaigns, there's very few that are really set up. We often have, frantic TOOs being submitted at that time, calls to your colleagues or your friends, etc. And there are other ATELs which come, interest starts to grow, and then email chains also start to grow. With people being brought in as more wavelengths are added. At the end of the day, there are email chains with hundreds of emails on there, with spotty crosstalk between them, not necessarily getting the best science out. And science almost evolves in real time, with some patchy success rate and missed opportunities. And I think many of us have been on these long email chains. I'm not necessarily arguing that is the worst thing to do. It's very exciting when that happens, but is that how our science can be optimized? So what are some of the missed opportunities? And I'm going to discuss just a few examples here. Please send me your own examples of missed opportunities. I'll be glad to hear more. One is, of course, just lack of preparedness. Now, this is not for want of trying, but rising phase XRB outbursts are often missed. And this is simply because, well, they're very fast. They evolve really, really quickly. This is one example of an outburst which is happening right now for U1543. You can see nothing for, I can't even remember how long ago was the last outburst, many, many years ago. And then suddenly it's found already in the soft state because it just evolves very, very quickly. The physics remains uncertain. The driver of these rising phase transitions remain uncertain. We've discussed how really a lot of effort needs to be put into understanding this phase. There are some efforts going on, looking at historical light curves, trying to understand the rising phase behavior, and also trying to actually catch it in multi-wavelength ways now when an outburst actually starts. So there are efforts going on. Other missed opportunities, lack of coverage, multi-wavelength coverage. This is V404 SIG 2015 outburst, multi-wavelength coverage compiled by Tom Marsh in this case. This was a spectacular outburst, one of the brightest outbursts in the past decade or so. There was a lot of intense coverage, which was organized remarkably quickly, actually, because this was a very short outburst. But you might notice that there are some important missing windows there. And not only that, but this outburst changed so quickly that even these gaps led to us missing a lot of science. One example here, I'm just going to show one example, which I am always really frustrated and fascinated by, is this the multivalent campaign that we had with NewStar and UltraCam. So this is optical light curve, and this is NewStar. This is very close to the peak of the outburst. And you can see here that we only had about 2,000 seconds of simultaneous coverage, or 2,000 times 2. And you can see here that there's a remarkable change of behavior across this gap here. So there's before this gap, there's the source is very, very soft in the hardness ratio. After the gap, it's suddenly flaring in hardness ratio, in flux, and also there were other changes that happened across this transition. In the radio, it zoomed up as well. The spectral index also changed. The cross correlation functions also changed. So there is definitely some remarkable change that happened. annoyingly, just as the pesky Earth got in the way. And what I really want to stress is that how short this was. This gap is only about 2,000, 3,000 seconds long. And yet there's a remarkable change of behavior which occurred during this transition. The only clue that we have of the instant of transition is this sort of sub-second or second flaring which happened, which we caught in the optical right in the middle. I'd really like to know more if we could, but hey, there was a natural gap. One could argue it's natural, it happened, what could we have done about it? But I would say that there are actually things which we can start to consider from a long-term perspective on how we don't miss out on such opportunities. Finally, I just want to say, how strict are these coordination requirements? Apologies if flashing lights you're uncomfortable with them. Please look away for just 30 seconds. So this has already been shown before. Using the WISE data, we saw some spectacular flaring in GX329-4. This is back in 2010. And you can easily see even by eye that this is the strongest flaring source in the entire field. This is at 12 micron wavelength, which is not usually associated with variability. But it's not just the flux variability which was remarkable. If you actually look at the multiple wavelengths that were covered by WISE, it's the spectral variability which is more remarkable. And two of these epochs, I think 3 and 4, were separated only by 11 seconds or so. Of course, the rest of the movie has been sped up. But that means that in just a few seconds, you can actually have important spectral variability. And usually we don't have this good coverage. If we didn't have this coverage, if we just took the average spectrum, for example, we could have ended up inferring something completely different about the behavior of the source. So in order to discuss some, these kind of missed opportunities and what we can do going forward, many of us had held a workshop at the Lorentz Center back in 2015, paving the way to simultaneous multiwavelength astronomy. The inception of this idea came from Matt Middleton. We got together in the Netherlands. You can see the weather is just like Cagliari, right? But it was a very productive week. We had lots of discussions. In particular, we had the involvement of several observatory directors, you can see there, and people who are really involved in some of these missions, key people. So it was very good to actually have them on board. There were two main outcomes, I would say. This is my own perspective, at least, that we came away with 3 main multi-wavelength legacy projects, which they weren't an outcome of the entire project, but collaborations evolved. And they were discussed with the directors. So 3 main projects came out, one on JWST, one with Chandra, the gold survey, led by Christian, and one on AstroSat, which several of us are leading a long campaign on GX329 and other sources. The other outcome was SMARTNet. So what is SMARTNet? SMARTNet is, I would say, a networking and collaborative tool. It's already been touched upon. You can find it here. It's hosted at the Integral Space Science Data Center. And it's really a way for us to sort of network with each other, to bring the community together, to bridge this gap between having these very formal consortia that we were talking about and having no collaboration at all. Really to ease pave the way for simultaneous multiwavelength astronomy in a way. The name comes from, I believe it was down to Greg Sivakov, who came up with the name finally. But I think the word network was important to us. We wanted it to be a bit more collaborative and not so formal. So this is just an example screen. It's almost like an ATEL. You post a message saying either a request for observations or just some information about what sort of outburst is happening, what sort of observations you are planning to do, etc. Okay, that you can also create a small timeline like this. It's a simple Google Sheet which you can enter. And then there's a timeline which comes up saying when various observatories and telescopes will observe any given source. So it really helps to ease that coordination. If you're on the mailing list, these are the sorts of emails that go out. This is an observation alert. This is by Carl Foster, who is one of our frequent posters, which is very nice. Coordinated multiwavelength observations of the Blazar 1ES, and then they list various details. This is another example from Giorgio talking about this transient which has been identified and a request for multi-wavelength observations. Okay, so in a sense, it helps to get the word out when an observation is about to happen, as opposed to an ATEL, which is almost post facto, essentially. At the moment, we have about 150 registered users across all wavelengths. There's been about 50 unique alerts and requests for follow-up, 10 publications acknowledged in SMARTNet so far. These are all approximate numbers. And there was some discussion yesterday. We haven't been using it or we haven't seen as much usage as we'd like. There are multiple reasons for this, of course. Partly the sky has been very quiet over the pandemic. We have also had other priorities over the past year or two. But there are also, more inherent things that we are still developing this platform. And recently, we have established a users committee with these early career scientists whose input is very important to us. And they have come up with a whole list of suggestions, which we're trying to implement, including, making the whole system much more user-friendly and allowing it to be much more streamlined. Of course, a lot of this is really time and effort limited. So, a lot of it is really being run just by Enrico Bozzo, who is, already very busy. And if you have any time or money or any interest in collaborating with the development, we'd be very eager to hear about this. There are other multi-wavelength tools as well, not necessarily collaborative, but I just want to let you know, in case you're not aware, well, hopefully everyone already knows about the viewing multi-wavelength tool from HISAC, which is very nice just for looking at schedules of, visibility of various targets using various observatories, including HST, at least one multi-wavelength observatory, and Swift as well, I guess. There's also Toby, which I discovered recently, which I like this tool, but I don't like the acronym, I have to say. But anyway, this is an integral tool, or at least, an ESA tool, and it comes up with a nice schedule for any given telescope, I guess, space telescope, and also lists the visibility of a target that you enter, which is nice. There are other tools as well. I won't have time to cover all of them. So one question that I think we should be thinking about at this stage is our science still in discovery mode at this stage? I think it was Martin Harwitt who made this argument, who has popularized it at least, that when you open up new regions of parameter space, then you end up making new discoveries. And this is a plot from his paper, his book, showing time resolution versus wavelength and how new discoveries have been made as more of this parameter space has opened up. This is a more modern version that we put together, showing wavelength and characteristic timescales and how X-ray binaries really cover a vast parameter space in this zone. But in terms of whether we are still in discovery mode, well, in many respects, yes. I think many of us would like to think so, at least ourselves. But we also have to acknowledge that we're not necessarily the new kid on the block anymore. And astronomers in other fields will not necessarily see us this way. So we really need to make the case for our field when we go out into the wide world, if you want, of proposing. So what can we do? Well, here are just some thoughts and suggestions. In terms of the infrastructure hurdles that we discussed, the obvious thing to do is to communicate with mission and observatory teams. If something is not possible, there's obviously usually valid reasons for this, but how far can we push some of the constraints of the missions? Often, it could be a software constraint, which can be circumvented. Hardware constraints or mission constraints are much more difficult, of course. For those, you have to be really involved at the inception stages of a mission. So if we're really thinking long-term here, really talking about the science that is important to us and how, even, minor changes to a mission might help enable completely new kinds of science, maybe serendipitously long-term. In terms of natural constraints, how do we get around visibility, uncooperative weather? I would say that, this is why we need multiple telescopes. We need redundancy. In terms of human constraints, these are perhaps the most difficult to overcome in many respects. And this is where it really is down to us. We do need to communicate with each other. We need to collaborate more, or at least network more, if collaboration sounds too much. That's the only way to build trust. And we were talking yesterday how building trust is the only way this sort of science really happens. People often say that chance favors the prepared. And so, you can be lucky, but only if you're prepared for it and willing to be prepared for it. Okay. But some other hurdles and opportunities, some of the biggest ones, are probably ahead for us. So we need to start thinking about systematics. We were discussing how our field is really rich in data, which is true. But when we enter that regime, then we start to enter the regime of data systematics. We need to understand.
5 minutes.
Thank you. We need to understand those better. We need to really get to grips with the models as well. What are the models telling us? What sort of testable predictions are the models really giving us? Of course, we've also discussed how our models themselves are quite complex. How do we communicate that complexity to proposal time allocation committees? It's important to get that message across in a simple way if you want. We also have new challenges nowadays with proposals being anonymized. Don't get me wrong, anonymization, I think, is exactly the right thing to do. But for those of us organizing, putting a lot of effort into multiwavelength campaigns, I think that creates some extra challenges. How do we, advertise all the effort that we're putting into these multiwavelength campaigns? But there are opportunities as well. I think it helps to have more synergy right from the start. We need to have synergy between theorists, numericists, to build in that collaboration. In terms of interpersonal hurdles, we need to think about early career progression and recognition in large collaborations. If we do move towards larger and larger collaborations, and maybe we can hear more from those of us involved in EHT, etc., how that is handled. Climate change. We will all probably be traveling less over the coming years, which is also perhaps maybe the right thing to do, even though, I would love to be there in Cagliari right now. But what does that mean in terms of networking? We all know that, a lot of these campaigns are often organized over a drink or just, informal discussions. How does that change? Another opportunity now is actually to bring in amateur astronomers in these sorts of networks. We can actually involve amateur astronomers much more integrally, and they do have an important role to play for many of these bright outbursts as we've seen recently. Scalability. Soon we will have large scale, large area synoptic monitoring, which is what we all want, of course, across multiple wavelengths. Conversely, there will be just too many of these sources to follow, and we might end up relying exclusively on serendipity. Serendipity is great, but not if we rely on it exclusively. There will be a lot of great archives to mine in the future. We shouldn't underestimate that. But there are also, I fear that there are a lot of gaps in there, and unless we know what we're looking for in the archives, many of these archives are also not public and may never be public. So I think we do need to get the word out about that. I probably don't have time to discuss this. Come back if you ask me a question about serendipity and archives later on, how we can optimize that. I'll come back to it later. As I'm ending, I just want to come back to this plot about new parameter space dimensions. Are we really opening up new parameter space here? So we have a lot of data at multiple wavelengths, and we are, probably maturing from the discovery stage, I would say. But at the same time, when it comes to at least multi-wavelength coordinated sort of science, I think that is still very new. And so instead of these two dimensions here, wavelength and time, I would argue that we actually need one more dimension, which is, excuse my crude three-dimensional attempt at this, but we need to add a third coordinated wavelength dimension. So you have wavelength, and time scale. And I would argue that in terms of this coordinated axis, where you have multiple wavelengths being coordinated on physically relevant timescales, I think this still remains largely unexplored, and we need to really keep that in mind and exploit this as much as possible. So this is my final slide. I thought I'd end on this one because this probably has some food for thought and discussion on it. These are the same, hurdles and opportunities that I talked about before. What can we do going forward? Well, already discussed a few things. There's no easy solution. Let me say that from the start. I think we can campaign for better campaigns. We need to make the case for our science. More than anything, I would argue that perhaps we are a relatively small community, and so we do need to have some consolidated community effort and networking. And on that note, I'm going to end. Thank you.
Thank you, Poshak, for being perfectly on time. Do we have any question in the room?
Not yet.
There are no questions on the Slack or in the Zoom. Oops, sorry about that.
We have a question now.
Okay. Stop. Sorry. Please go ahead. Yeah.
Hi, Poshak, this is Vicky. Thanks for the very, very nice talk. I was wondering that you mentioned that we have like 2 examples of great multi-wavelength campaigns with the EHT and the gravitational wave follow-up stuff. Is there something we can learn from there? Or is it just the fact that they had the advantage of being so new that they got, excuse me, that they got all these multi-wavelength campaigns organized and accepted on various observatories?
Okay, thank you, Vicky. Great question. So I think this is better answered by others who are actually in those campaigns, like Sarah, I believe. But my own take is that, yes, we absolutely should look at them and try to learn from them. Sorry, I'm not going to go back all the way. But basically, I would argue that those really worked because, of course, they opened up completely new parameter space. Okay, so they were really new regions of parameter space that they probed. Secondly, they were planned, many years in advance, so there was a long lead time, of course. In terms of, difficulties faced inside those campaigns, this is better argued by others, but we do need to think about how that affects people's career progression, etc. What kind of science came out. I would argue that the science which is coming out is amazing, is fantastic. At the same time, it's not obvious to me that we are associating that science with any particular person, if you know what I mean. And maybe that's the way to go going forward. We need to think about how people are recognized for the work that they do. Yeah, and maybe others can contribute at this stage.
Greg, you had a question?
Muted.
This was more a external perspective on what worked about EHT and what worked about the gravity wave. And I think they've taken a lot of clues from the particle physics community about how to perform collaborations across multi-institutions, multiple countries. And I think, both to the good and to the bad, but a lot of us are involved in physics departments, and we have these resources where we can actually talk to the particle physicists to get an idea of how these are working, how they're not working. And I think that's something we really, if you have that opportunity, you really need to be doing to figure out then how we want to make progress.
Yep, thank you.
Maybe I take the opportunity as a chairman. I'm not sure it's a question or a comment, but I'm part of a collaboration for a mission that will be launched in 2022, which is SVOM, with it's French-Chinese or Sino-French. And I was wondering, or maybe commenting, that one of the way is maybe thinking automatization, like, Swift, there's an alert on board and the platform decides to switch immediately to the target. It's what we're going to do with SVOM, involving ground telescopes that are part of the project. I mean, infrared, optical telescopes. And maybe one way to go and to be able to catch early phases, very early phases of any transient is automatization. What do you think of that?
Yeah, I think that's a great idea. Absolutely, that's the way to go. I mean, hopefully this will become a little bit easier with things like LSST going forward anyway. But even there, the cadence is not yet decided. There will be gaps. So I think there's definitely more scope to do. And I definitely agree that roboticization, using robotic telescopes is the way to go with some of that. Yes. It's too early in the morning here, sorry.
Thank you. If we don't have any more quick questions, then we can thank Poshak again.
Thank you.